Hello, good day everyone. Welcome to my class. This is teacher Roswin and I will be your teacher for this subject. We will have the science and the universe, a brief tour. We invite you to come along on a series of voyages to explore the universe as astronomers understand it today. Beyond Earth are vast and magnificent realms full of objects that have no counterpart on our home planet. Nevertheless, we hope to show you that the evolution of the universe has been directly responsible for your presence on Earth today. Along your journey, you will encounter science and the universe, a brief tour. A canyon system so large that on Earth it would stretch from Los Angeles to Washington, D.C. A crater, and other evidence on Earth that tell us that the dinosaurs and many other creatures died because of a cosmic collision. A tiny moon whose gravity is so weak that one good throw from its surface could put a baseball into orbit. A collapsed star so dense that to duplicate its interior we would have to squeeze every human being on Earth into a single raindrop. Exploding stars whose violent end could wipe clean all of the life forms on a planet orbiting a neighboring star. A cannibal galaxy that has already consumed a number of its smaller galaxy neighbors and is not yet finished finding new victims. A radio echo that is the faint but unmistakable signal of the creation event for our universe. Such discoveries are what make astronomy such an exciting field for scientists and many others. But you will explore much more than just the objects in our universe and the latest discoveries about them. We will pay equal attention to the process by which we have come to understand the realms beyond Earth and the tools we use to increase that understanding. Now, what is astronomy? It is defined as the study of the objects that lie beyond our planet Earth and the processes by which these objects interact with one another. We can now take a brief introductory tour of the universe as astronomers understand it today to get acquainted with the types of objects and distances you will encounter throughout this lesson. We begin at home with Earth. Our nearest physical planet, about 13,000 kilometers in diameter. A space traveler entering our planetary system would easily distinguish Earth from the other planets in our solar system by the large amount of liquid water that covers some two-thirds of its crust. If the traveler had equipment to receive radio or television signals, or came close enough to see the lights of our cities at night, she would soon find signs that this watery planet has sentient life. Our nearest astronomical neighbor is Earth's satellite, commonly called the Moon. This figure shows Earth and the Moon drawn to scale on the same diagram. Notice how small we have to make these bodies to fit them on the page with the right scale. The Moon's distance from Earth is about 30 times Earth's diameter, or approximately 384,000 kilometers. And it takes about a month for the Moon, Earth, revolving around our star, the Sun, which is about 150 million kilometers away. Approximately 400 times as far away from us as the Moon. We call the average Earth to Sun distance as astronomical unit, or AU, because in the early days of astronomy, it was the most important measuring standard. Light takes slightly more than 8 minutes to travel 1 astronomical unit, which means the latest news we receive from the Sun is always 8 minutes old. The diameter of the Sun is about 1.5 million kilometers. Earth could fit comfortably inside one of the minor eruptions that occurs on the surface of our star. If the Sun were reduced to the size of a basketball, Earth would be a small apple seed about 30 meters from the ball. Earth is only one of the 8 planets that revolve around the Sun. These planets, along with their moons and swarms of smaller bodies such as dwarf planets, make up the solar system. A planet is defined as a body of significant size that orbits a star and does not produce its own light. If a large body consistently produces its own light, it is then called a star. The Sun is our local star, and all the other stars are also enormous balls of glowing gas that generate vast amounts of energy by nuclear reactions deep within. We will discuss the processes that cause stars to shine in more detail later in our discussion. The other stars look faint only because they are so very far away. If we continue our basketball analogy, Proxima Centauri, the nearest star beyond the Sun, which is 4.3 light-years away, would be almost 7,000 kilometers from the basketball. When you look up at a star-filled sky on a clear night, all the stars visible to the unaided eye are part of a single collection of stars we call the Milky Way Galaxy, or simply the galaxy. Our galaxy looks like a giant disk with a small ball in the middle. If we could move outside our galaxy and look down on the disk of the Milky Way from above, it would probably resemble the galaxy in the figure, with its spiral structure outlined by the blue light of hot adolescent stars. The Sun is somewhat less than 30,000 light-years from the center of the galaxy, in a location with nothing much to distinguish it. From our position inside the Milky Way Galaxy, we can see through to its far rim, because the space between the stars is not completely empty. It contains a sparse distribution of gas, mostly the simplest element, hydrogen, intermixed with tiny solid particles that we call interstellar dust. This gas and dust collect into enormous clouds in many places in the galaxy, becoming the raw material for future generations of stars. This figure shows an image of the disk of the galaxy as seen from our vantage point. Recent observations, however, have also revealed a rather surprising and disturbing fact. There appears to be much more to the galaxy than meets the eye. From various investigations, we have evidence that much of our galaxy is made of material we cannot currently observe directly with our instruments. We therefore call this component of the galaxy dark matter. We know the dark matter is there by the pull its gravity exerts on the stars and raw material we can observe. But what this dark matter is made of and how much of it exists remain a mystery. Furthermore, this dark matter is not confined to our galaxy. It appears to be an important part of other star groupings as well. At distances of 10 to 15 million light-years, we find other small galaxy groups, and then at about 50 million light-years, there are more impressive systems with thousands of member galaxies. We have discovered that galaxies occur mostly in clusters, both large and small. Some of the clusters themselves form into larger groups called superclusters. The local group is part of a supercluster of galaxies called the Virgo supercluster, which stretches over a diameter of 110 million light-years. We are just beginning to explore the structure of the universe at these enormous scales and are already encountering some unexpected findings. At even greater distances, where many ordinary galaxies are too dim to see, we find quasars. These are brilliant centers of galaxies glowing with the light of an extraordinarily energetic process. The enormous energy of the quasars is produced by gas that is heated to a temperature of millions of degrees as it falls toward a massive black hole and swirls around it. The brilliance of quasars makes them the most distant beacons we can see in the dark oceans of space. They allow us to probe the universe 10 billion light-years away or more, and thus 10 billion years or more in the past. The universe is very small. On average, the universe is 10,000 times more empty than our galaxy. Yet, as we have seen, even the galaxy is mostly empty space. The air we breathe has about 1,019 atoms in each cubic centimeter, and we usually think of air as empty space. In the interstellar gas of the galaxy, there is about one atom in every cubic centimeter. Intergalactic space is filled so sparsely that to find one atom on average, we must search through a cubic meter of space. Most of the universe is fantastically empty. Places that are dense, such as the human body, are tremendously rare. The most abundant elements in the cosmos today are listed in this table. Physicists have discovered that everything that happens in the universe, from the smallest atomic nucleus to the largest superclusters of galaxies, can be explained through the action of only four forces: gravity, electromagnetism, which combines the actions of electricity and magnetism, and two forces that act at the nuclear level. The fact that there are four forces and not a million or just one has puzzled physicists and astronomers for many years, and has led to a quest for a unified picture of nature. Much to your surprise, a member of the Flat Earth Society moves in next door. He believes that Earth is flat and all the NASA images of a spherical Earth are either faked or simply show the round disk of Earth from above. How could you prove to your new neighbor that Earth really is a sphere? Today, few people really spend much time looking at the night sky. In ancient days, before electric lights robbed so many people of the beauty of the sky, the stars and planets were an important aspect of everyone's daily life. All the records that we have, on paper and in stone, show that ancient civilizations around the world noticed, worshipped, and tried to understand light in the sky and fit them into their own view of the world. These ancient observers found both majestic regularity and never-ending surprise in the motions of the heavens. Through their careful study of the planet, the Greeks and later the Romans laid the foundation of the science of astronomy. This time, we will have Chapter 2, Observing the Sky, the Birth of Astronomy. The celestial sphere. Our senses suggest to us that Earth is the center of the universe, the hub around which the heavens turn. This geocentric, Earth-centered view was what almost everyone believed until the European Renaissance. After all, it is simple, logical, and seemingly self-evident. Furthermore, the geocentric perspective reinforced those philosophical and religious systems that taught the unique role of human beings as a central focus of the cosmos. However, the geocentric view happens to be wrong. One of the great themes of our intellectual history is the overthrow of the geocentric perspective. If you go on a camping trip or live far from city lights, your view of the sky on a clear night is pretty much identical to that seen by people all over the world before the invention of the telescope. Gazing up, you get the impression that the sky is a great hollow dome with you at the center, as shown in this figure, and all the stars are an equal distance from you on the surface of the dome. The top of that dome, the point directly above your head, is called the zenith, and where the dome meets Earth is called the horizon. From the sea or a flat prairie, it is easy to see the horizon as a circle around you, but from most places where people live today, the horizon is at least partially hidden by mountains, trees, buildings, or smog. If you lie back in an open field and observe the night sky for hours, as ancient shepherds and travelers regularly did, you will see stars rising on the eastern horizon, moving across the dome of the sky in the course of the night, and setting on the western horizon. Watching the sky turn like this night after night, you might eventually get the idea that the dome of the sky is really part of a great sphere that is turning around you, bringing different stars into view as it turns. The early Greeks regarded the sky as just such a celestial sphere, just like in the figure. Some thought of it as an actual sphere of transparent crystalline material, with the stars embedded in it like tiny jewels. That's all for this session. I hope you learned something. Thank you and have a great day. See you soon. Bye.